friends, welcome to the online lecture of the subject M. Today we will study about the topic Advanced and Miscellaneous Metrology Part 1. The first topic with which we should start is laser and precision instrumentation. We know that laser is known as light amplification by stimulated emission of radiation. In laser, the rays of light are focused onto a very small area, or we can say that they are the rays of the light which are parallel to a very high degree. There are many types of laser, but the particular kind of laser that we are going to study is helium neon gas laser. Let us study about the laser transducer system. First of all, let us check the figure of the laser transducer system. Okay, here is the figure of the laser transducer system. There are four main parts of the laser transducer system. First one is laser, then after interferometer, then reflector, and the last one is receiver. We will check all the parts one by one. The first one is laser. Here it should be noted that the laser used is a double frequency helium neon laser. There are two frequencies, F1 and F2. Two frequencies separated by their polarization state. Here two frequencies are separated by their polarization state. First frequency F1 is used for measurement purpose and it is going to measurement reflector. Second frequency F2 is used for reference purpose and it is going to reference reflector. Now, when there is a movement in the measurement reflector, this will cause the frequency shift of delta F1. Here, due to the movement of the measurement reflector, there will be shift in the frequency by value delta F1. It is the printing mistake. Here the value should be delta F1. Now this difference is proportional to the displacement. The difference in the frequency is directly proportional to the displacement, and thus we can find the value of displacement, and the direction can also be found from the sign of the signal difference. Now comparison is electronically processed to generate the displacement data in this phase detector. It should be noted that laser can measure up to 6 independent axes of displacement using only one transducer. Next and very important topic is coordinate measuring machines, that is also known as CMM. CMM is capable of measuring in all three orthogonal axes. We know that orthogonal axis is X, Y and Z axis. It is the integration with a computer. You can compare it with CNC machine. It can generate 3D object as well as to carry out the complex mathematical calculation with precision and speed. So these are the uses, or you can say the advantages of CMM. Let us check about the structure of the CMM. The basic version of CMM has a 3 axes along 3 mutually perpendicular directions. Thus the work volume is cuboidal. A carriage is provided for each axis which is driven by a separate motor. When the probe makes contact with the workpiece, the computer captures the displacement of all 3 axes. Now depending on the geometry of the workpiece being measured, one can choose any of the 5 popular physical configuration. Now we'll check the physical configuration one by one. Okay, this figure shows a cantilever type CMM. The vertically positioned probe is carried out by a cantilever arm. The probe moves up and down along the Z axis, whereas the cantilever arm moves in and out along Y axis. The longitudinal movement is provided by the X axis, which is basically the work table. This configuration is very easy to load and unload the workpiece, but more sensitive to errors. Second one and important one is moving bridge type. As the name suggests, the probe unit is mounted on a horizontal moving bridge. It is a good choice if better rigidity is in the structure is required. The third one is column type. This provides very good rigidity and accuracy. This configuration is often referred as universal measuring machine. One is horizontal arm type. This structure is suited for large and heavy jobs, and in this type of CMM the probe is carried out by the horizontal axis. And the last one is gantry type. This is a kind of structure which is used for very large workpieces. In this type of structure, the operator can walk along with the probe. The support of the workpiece is independent of X and Y axis. Let us check all the structures at same time. First of all, we have studied about the cantilever arm type structure. Then the second one and important one is moving bridge type. Then the third one is column type. It is also known as the universal one. Then the fourth one is horizontal arm type, which is used for heavy jobs. And the last one is gantry type, and it is used for very large, very heavy workpiece. Now we will see the modes of operation. The first one is manual. In manual CMM, it has free floating probe that the operator moves along the machine's 3 axes to establish the contact with the part features. The difference in the contact positions are the measurements here. The second one is semi-automated. It provides with an electronic digital display for the measurement. Many functions such as setting the datum, change of sign, and the conversion of dimensions from one unit to another are done here electronically. So it is called semi-automated. And the third one is computer controlled. Computer controlled machines have an onboard computer which increases the convenience and reliability. They are quite similar to CNC machines in the control and operation. Next thing is probe and its assembly. The figure shows probe and the assembly. Here the probe is connected with the probe head, and probe head is directly connected to the structure of the CMM. At the end of the probe there is a stylus. This stylus is the main sensing element of this wall assembly. Sometimes this stylus is a kind of LVDT structure that we have already studied in the previous chapters. See about the operation of the CMM. A computer offers a high degree of versatility, convenience, and reliability in the CMM. The modern CMM is very similar in the operation to a computer numerical control machine, that is CNC machine, because both the control and measurement cycle under the control of the computer. Now there are 3 types of command in the software of a CMM machine. The first one is move commands. Move commands direct the probe to the data collection points. The second one is measurement commands. Measurement commands result in the comparison of distance traversed to the standard built into the machine for that axis. And the third one is formatting command. Formatting translates the data into the form desired for the display or printout. So briefly we can say that the first one is the used for movement of the probe, the second one is for measuring the distance, and the third one is display the data. Let us check the applications of CMM machines. The first one is to check the dimensional accuracy of NC produced workpieces. We can measure the dimensional accuracy of the workpieces that has been produced by the NC machines. Then after, it is ideal for determination of shape and position, maximum metal condition linkages of the results, etc. Then after, CMM machines are used for the safety components as for aircraft and space vehicle. And the last one is, it is used for reverse engineering. We know that a complete 3D geometric model with all critical dimensions can be built where such models do not exist. Once the geometric model is built, it becomes easier to design dies or molds for the manufacturing operations. So CMM is very useful in the reverse engineering. The next topic is optical measuring techniques. The first device is tool maker's microscope. The second one is profile projector, and the third one is optical square. We'll see all these devices one by one. Now we will study about the tool maker's microscope. This is the figure of the tool maker's microscope. First of all, we will see the construction of tool maker's microscope. Tool maker's microscope consists of a heavy hollow base. The work table is mounted on the base of the instrument on cross slides, and it is equipped with the accurate micrometer screws to move it in two mutually perpendicular directionals in the horizontal plane, that is X and Y. This table can be rotated through the 360 degree, and the angular rotation can be read by a fixed vernier with a scale of 3 minutes. The optical head is mounted on a vertical column and can be moved up and down and focused over the work. The clamping screw is provided to clamp the optical head at any desired position. At the top of the optical head, the eyepiece unit carries different eyepieces, any one of which can be used at a time. Now we will see the working of the tool maker's microscope. The component to be measured is mounted on a glass plate placed on the table. A light source provides horizontal beam of light which is reflected from a mirror by 90 degree upwards toward the table. A shadow image of outline of contour of the workpiece passes through the objective of optical head and is projected by a system of 3 prisms to the ground glass screen. Observations are made through the eyepiece of the optical head. The direction of light source can be tilted with respect to workpiece by tilting the measuring head and the whole optical system. This inclined light source is necessary in some cases, as in screw thread measurements. Now, measurements are made by means of cross lines engraved on the ground glass screen. The screen can be rotated through 360 degree and the angle of rotation is read. Different types of graduated and engraved screens and corresponding eyepieces are used for measuring different elements. For example, a revolving screen for measurement of standard thread will contain all the basic profile of all standard threads in various pitch ranges and also various included angles of the thread. Now we will see the applications of tool maker's microscope. The first one is the determination of relative position of various points on a work. On a workpiece, we can determine the relative position of various points by using a tool maker's microscope. The second one is measurement of angles by using a protector eyepiece. If we use a protector type eyepiece from the set of various eyepieces, we can measure the angles by using tool maker's microscope. Third one is comparison of thread forms, and the last one is comparison of an enlarged projected image with a scale tracing fixed to the projection screen. So these are the applications of a tool maker's microscope. The next one is profile projector. Profile projector is an optical device which is used to check the profile of the components having special formed surfaces such as gears, screws, and those objectives having regular or irregular profile. It is also known as optical projector. It is highly sophisticated and a versatile optical instrument which is designed as per international standards. Now, let us check the figure of the profile projector to check its construction and working. This is the figure of a profile projector. The workpiece to be inspected is mounted on a table such that it is in line with the light beam coming from the light source. In most projectors, the table can be moved in two mutually perpendicular directions in the horizontal plane, that is X and Y direction. The movement is effected by operating a knob attached with a double vernier micrometer, which can provide positional accuracy of up to 5 micrometer or better than 5 micrometers. The light beam originating from the lamp is condensed by means of condenser and falls on the workpiece. Now, the image of this workpiece is carried by the light beam, which passes through a projection lens. This is the projection lens. The projection lens magnifies the image, which falls on a highly polished mirror capped at an angle. This one is the highly polished mirror that is capped at an angle. The reflected light beam carrying the image of the workpiece now falls on a transparent screen. This one is the transparent screen. The location of the screen should be such that it provides an accurate magnification and perfectly confirms the measurement indicated by the micrometer. A reticle attached to the end of the projection lens provides image of two mutually perpendicular cross wires, which can be used for the purpose of the measurement. Many projector screens can also be rotated about the center, thereby enabling the measurement of angular surfaces also. This is the application of a profile projector. A rapid inspection of linear and angular measurements of small to medium sized components such as gears, tools, rubber components, electronic assemblies, tool wear, etc. can be done by the profile projector. Now we will study the third one, that is optical square. Optical square is used for turning the line of the sight by 90 degrees from its original path. An optical square is essentially a pentagonal prism. Regardless of the angle at which the incident beam strikes the face of the prism, it is turned through 90 degrees by internal reflection. Now let us check the figure of the optical square. The figure shows the use of an optical square to test the squareness. The axis of the incident beam from the autocollimator forms the measuring data. This is the autocollimator. An optical square is utilized for turning the incident beam through exactly 90 degrees. Here it is turning 90 degrees by this optical square. This optical is nothing but a pentagonal prism. In this test, it is assumed that two surface faces are perfectly straight. A stainless steel mirror block with flat base is used for the horizontal surface for aligning the collimator with the surface. A reading is thus taken in collimator at position A. This is position A. The mirror with the base is then transferred to the vertical surface and the optical square placed in the angle is indicated. Another reading is taken in the position B. Here position B. The difference between two readings would be the squareness error, not taking made of its direction. So this is how we can measure the squareness using the optical square.